welcome to 15.6 to 15.9. Now we're going to talk about pendulums. Okay, and the first slide there with the chart, the main thing to see there is that when you're dealing with small angles, the angle measure is very close to sine of that angle. Angle measurement in radians is close to the angle sine of that angle. And so really, when we talk about pendulums, the angle not mattering, that's only true for small angles. And so because of the small angle approximation, that's why the whole thing with pendulums works, and their oscillations. And you see the derivation in the next couple of slides where, so that means that x is about s, the arc length, the distance that it moves, the straight line distance is pretty close to the arc length. And so if that's the case, then dx dt is about ds dt, and tangential acceleration is about the second derivative of the arc length with respect to time. And so with that approximation, what we end up with is negative g over L. G is the acceleration due to gravity, and L is the length of the pendulum. Because, sine of S over L, the arc length over the length, all that stuff, that is about equal to the second derivative of the arc length with respect to time. And because of that, again, now that's the differential equation for a wave, for simple harmonic motion. And then, what that was, right, remember, negative omega squared x equals the second derivative of x with respect to time. That means that omega squared is equal to g over L. Right? So then for a simple pendulum, omega is equal to the square root of g over L, just like omega was the square root of m over k, or k over m with pendulums, or springs. Frequency is omega over 2 pi, so f is 1 over 2 pi times root g over L, and the period is 2 pi root L over g. So then, if we have a simple pendulum, and it's suspended from the ceiling of an elevator, what would happen if the elevator is moving up at a constant velocity? What would happen to the period? Nothing. Constant velocity means that everything is in equilibrium, and it's as if the pendulum was just sitting on a floor that wasn't moving at all. If the elevator is moving down at a constant velocity, again, no change in the period. Okay. If the elevator is accelerating upward, then what's happening? Really what we're doing there is we're increasing g. And if we increase g, then that is going to decrease the period, right? It's gonna go faster. And you can see that in the equation. If g increases, t is 2 pi root L over g. Right? If g increases, t is going to get smaller. If the elevator is moving up but slowing down, if it's on its way up but slowing down, that means the acceleration is downward. And so there g is decreasing. We've decreased g. That means the period is going to increase. When it goes up to the side, it's as if there's not as much force pulling it back down, and so it's a longer period to pass through. Again, if the elevator is accelerating downward with an acceleration less than g, if it was more than g, that would mean that it's being pushed down, and then the pendulum wouldn't swing at all. But here, t is going to increase. Again, it's the same thing if it's moving up or moving down. As long as it's accelerating downward, g is effectively decreasing, and so the period is going to increase. If the elevator cable broke and the whole thing was just falling, you can imagine taking a pendulum apparatus and just dropping it. What's the period of the pendulum, Bob? Like infinity. Because there's nothing holding it up in order for it to swing. There's no tension in the rope. And so the period was approached infinity. I don't have use of the room, so we got to get creative here. Okay, so the first example, a pendulum whose period is 1 second on Earth is taken to the moon. Calculate the period of the pendulum on the moon. All right. So the acceleration due to gravity on the moon is about 1.6 meters per second squared, right? And then the period on Earth is 1 second. So what we need to find here is the length of the pendulum. And so t is 2 pi root L over g. One way to remember this, right, radical legs, It's like a pendulum is like a leg, kind of. So the period is 2 pi root L over G. Pi has 2 legs, whatever. It's corny, but it might help you remember. We need to solve here. So this is going to be T over T times, no, T over 2 pi squared. And then I multiply G over here times G equals L. So this is 1 and this is 9.8. So if we plug those numbers in, we end up with L is about 0.25 meters. Right, so now we plug this in for the moon. And so T equals 2 pi root L over G on the moon. So we've got 2 pi root 0.25 over 1.6. But we get that the period will be about 2.5 seconds. So what's the relationship here? You know, this is about 1/6 of the gravity on Earth. And then if you take this, so this is like taking the period and multiplying it by the square root of 6, which will be about 2.5. So the other one, the abstract simple problems, is that kind of thing. If I change the length, if I change G, if I, the frequency, then, or just looking at the length rather, how will that affect the period and the frequency? Right. Again, our relationships here, T equals 2 pi root L over G, and F is 1 over 2 pi root G over L. All right, so for A, if I have, well, A is L, T, and then F. B, if I have half the length of the pendulum, then how is that going to change this? Well, half the length, that's going to be then T times the square root of 0.5, right? Because this is 0.5 L, so then I have the square root of 0.5. And then the frequency would be F over the square root of 0.5, because I'm putting 0.5 down in here. What about C? C gives us 2T. So in order for the period to double, that means that the length actually has to be 4 times as much, 4L. And then when I flip this, F is also equal to 1 over T. So that means I'm going to have half the frequency, F over 2. All right, and then for D, it's like I'm taking the frequency and I'm doubling the frequency. Well, if I double the frequency, I cut the period in half. And then in order to get 2F, then I have to have 1/4 of L. Right, I'm going to put 1/4 in there. That'll end up doubling this whole thing. So I've got L over 4. Back. Okay. Now for physical pendulums. If you have a physical pendulum, what we're talking about is a solid object that's pinned somewhere and then is swinging, kind of like we did on the first day of class with the center of mass thing, except we weren't looking at those things as they were swinging. And so here, one thing that's important to note in the derivation, d is the length from the axis of rotation to the center of mass. So d is a distance as we look at that. And so this involves torque. Remember, torque is the force, R cross F. And so that's going to be d, that distance, times the force is the acceleration due to gravity, mg, and then sine theta. So that's how we do R cross F here. And then that is going to be equal to I alpha, but alpha is d theta dt. And so, remember that sine of theta with small angles is about theta. So sine of theta gets replaced with theta. So the formula looks like negative gmg theta equals I d squared theta dt squared. And then again, that's the differential equation where omega squared is equal to dmg over I. If you take I and you bring it to the other side, then you have negative this thing times theta equals the second derivative of theta with respect to time. And so omega squared is dmg over I. And our equations then for a physical pendulum, omega is the square root of dmg over I. The frequency is 1 over 2 pi times dmg over I. This is the damage equation, by the way, right? Root damage over I. And then period is 2 pi root I over damage, dmg. And then this is an experiment that we can do in class. We can take a meter stick, pivot it about one end, and use a stopwatch to time the motion for 10 oscillations. And then you can calculate the period and the theoretical period. And that should match up. Okay, simple harmonic motion and uniform circular motion. This is where if you take a circle, you, as the circle goes around, if you were to keep track of the position with respect to time, the velocity with respect to time, the acceleration with respect to time, that would give you simple harmonic motion. If you pay attention to, as it moves in one dimension back and forth. Okay, damped oscillations. Damped oscillations are where we have a spring or a pendulum and there's friction. So the amplitude is decreasing over time. And you can see in the graph that what we have is, it looks like our regular sine graph, cosine graph for the period. But what's happening is the amplitude is decreasing over time. And so eventually, given enough time, those would just go down to 0. And this also, right, it's pretty rare you're going to see something like this, but you should at least see it and understand it and do some problems with this. And you can see that omega then becomes the square root of k over m minus b squared over 4m squared. And x, because the whole period is the same as before, the amplitude cosine omega t plus phi, and then, but it has that a formula very familiar to us, where e to the negative bt over 2m, which gives us the rate at which that motion is decreasing due to the forces of friction. Okay. Forced oscillations and resonance. This, again, is something that you've seen before, and this is all we're going to talk about it. It's just something you need to be familiar with. All mechanical structures have one or more natural angular frequencies. In other words, a frequency that, like, if you hit it, that's the sound it would make. That's one way to find what the natural frequency is for that thing. And if you force something, then what happens is it resonates inside of that, and it'll just build and build and build. And that's called resonance. And that's it. We won't make this any longer than we have to. One more thing. Now that we've completed chapter 15, you have now completed the entire first semester of a university physics course. So, congratulations.